Good day, my name is Ernst Bekker, product specialist of cyclones at Multotec. The discussion on this specific topic revolves around hydrocyclones. It's not a training session and it's not a sales presentation. It is just to illustrate sometimes why the hydrocyclone can bring joy to people's lives or it can become a frustrating piece of equipment. So the topic on this presentation, hydrocyclones, blessing or curse. We're going to have a look at some applications and what are some of the problems that has been observed. It is by no means covering all aspects, but it's just to plant the seed, to say be careful. So in this presentation, I'm going to briefly look at the principle of operation. How do we characterize the performance of the hydrocyclone? And then briefly touch on the general duties. There are 4 main general duties, each one will be briefly discussed. So the principle of the hydrocyclone. Feed, solids mixed with slurry or water forms a slurry. It enters the hydrocyclone in a tangential format, and as the rotational motion starts, the fine material migrates to the center of the cyclone and leaves via the overflow, and the coarse material migrates to the outside of the hydrocyclone and moves downwards through the spigot. In people's minds, the hydrocyclone should be a perfect classifier, and this is what perfect classification looks like. The cut point of the hydrocyclone is defined as the percentage, the 50% probability of a particle size reporting either to overflow or to underflow. On the curve that you see on the presentation, the left-hand side is the fine fraction and the right-hand side the coarser fraction. As you can see on the y-axis on the left-hand side, it is recovery to underflow. In reality, this is the type of separation that starts to take place, with the cut point at the 50% mark. Because we are not achieving perfect separation, there are particles that is getting misplaced. We have coarse particles being misplaced to the overflow, and we have fine particles being misplaced to the underflow. An additional factor that plays a role is the bypass water, which is shown on the left bottom hand side of this graph, and we refer to that, as I said, the alpha water or the bypass water. You can never have no water in the underflow, and the more water you have in the underflow, the more fines is reporting to the underflow. Because of that, we as suppliers have to discount the alpha water or the bypass water effect, and we use a curve that we refer to as the corrected separation curve. There are therefore 2 different cut points that we as suppliers use. There's a D50 actual cut point, and in our simulations we refer to the D50 corrected cut point. The objective in hydrocyclone classification is to have the unit operate as efficiently as possible. The fact that there is material reporting to the overflow and underflow does not mean that the unit is operating efficiently. On the graph that you see in the presentation, there is a red line which shows the overflow size distribution of a hydrocyclone operating efficiently. There's a dotted line showing the overflow size distribution of a hydrocyclone that's not operating efficiently. And then the third curve, which is the green one, flotation recovery response per particle size. When you look at the economic effect, and this was based for copper ore, and the difference between a cyclone with a low efficiency and high efficiency, as you can see, the economic impact on a yearly basis is quite significant. This is for illustrative purposes, and it will differ from process to process. So one may think that the hydrocyclone is operating correctly, unknowingly you are losing money. And further down this presentation, I'll show you some of basic factors that we can keep in consideration to improve the hydrocyclone performance. The general duties of a hydrocyclone are mainly classification, desliming and dewatering. Classification, roughly about 70% of the mass is reporting to the underflow. Desliming, about 90% of the mass reporting to the underflow, assuming the other 10% is slimes. And then on dewatering, 95% of the mass reporting to the underflow. Obviously, one would like to have approaching 100%, but that's not always practical. So looking at classification then, as the word indicates, classification is classifying the particle size into different size fractions, similar to the screen shown on the picture on the left-hand side. Oversize goes one direction and the size in a different direction. And the same happens on the hydrocyclone, where the overflow is the finer fraction and the underflow the coarser fraction. As I mentioned, roughly 75% of mass recovered to the underflow is assumed if we don't have a particle size distribution. If we have a particle size distribution, that value can change. It's a sizing activity, and it's used normally where it's not economical to use ultrafine screening or where there's no screen apertures available. The hydrocyclone normally falls in the category between 0 and 150 microns. And that is where the classification actions then normally takes place via a hydrocyclone. There are various positions of hydrocyclones in a process flow sheet. The flow sheet that you're looking at is that of a platinum process. You will see there are some other cyclones that's not circled by the white circles. That will be discussed during this presentation, except for the cyclones in the center of the presentation, which is called dense media cyclones, and that does not form part of this presentation. The cyclones that's circled in white is then indicating the different applications in the process where the hydrocyclone can be used. So why does the hydrocyclone sometimes provide results that you as a client do not want? One of the main reasons is when you've got a size distribution, as shown in this table. A sample has been screened at different size fractions, and if you as a client decide that you want to separate just above 53 microns, everything below 53 microns should go into one direction, and everything above 53 microns should go in a different direction. In addition, you want a mass split of roughly about 20% going then with the fine fraction. So what you're looking for is the perfect separation. On this graph, it's illustrated by this vertical line. I've used 50 microns just as a rounded down number. So everything minus 50 micron should report to the overflow, and everything plus 50 micron to the underflow. As mentioned earlier in the presentation, the actual separation curve of the cyclone looks like this, where there is misplaced material of both coarse and fines. The hydrocyclone is not a perfect classifier. So because of this misplaced material, you now have in the overflow up to 70 micron material. In the underflow, where you in your mind thought there's going to be no fines, you're going to have around 35, between 50 and 35 micron material. But remember, the underflow is wet, and therefore there's the bypass water effect as well, which is also carrying fines to the underflow. So the reality of the hydrocyclone is that you can never have no fines in the underflow. We can, however, minimize the amount of coarse material that reports to the overflow, but your reference needs to be similar to that of the supplier. When you indicated to the supplier that the cut point that you wanted was 53, or in this example 50 microns, we as a supplier use the D50 corrected cut point. We assume that you want at 50 micron particles to have a 50% probability of reporting either to overflow and underflow, and therefore we select the hydrocyclone based on that premises. That results then in some of the coarse material reporting then to the overflow. If you have specified that you don't want any 50 plus 50 micron material in the overflow, the curve and the selection process would have been vastly different. The cut point of the hydrocyclone becomes much finer. Obviously you're going to have more fines also in the underflow. But that is then ensuring that you don't have any misplaced coarse material in the overflow. This problem looks quite simplistic, but in reality it has caused big problems already in the industry. In this example, the cyclone on the left hand side was selected based on the premises of a cut point of 250 microns. There was a misunderstanding, and when the client realized that the reference that is used was incorrect, it resulted in a very different approach in terms of cyclone selection. As you can see on the picture on the right hand side, the cyclone diameter has become much smaller. It is possible, when there is a problem on the hydrocyclone, that there's modifications that can be made to the existing design. Cone angles can be changed, vortex finders can be changed. So the cut point of the hydrocyclone can be changed to a certain extent. But if the basis of selection, the starting point, if that was wrong, then most probably you will have to look at a different cyclone diameter. Moving on to desliming. On desliming, we assume 90% of the mass to report to the underflow. As a rule of thumb, if no size distribution is available. If the size distribution is available, that value can change again. It's the removal of ultra fine material that we are after. But this ultra fine material or slimes, we normally assume to be in the range of between 15 and 45 micron material. However, each industry defines slimes in a different size fraction or as a different reference. So it's important when you speak to the supplier that when you use the word slimes, that you just illustrate what size fraction you are referring to. The desliming cyclones is used in processes where the fines is not suitable or can create problems in the processes that will follow the hydrocyclone. Like for example, spirals and flotation. The cyclone configuration is also different to that of classification. Again, referring to the flow sheet, the desliming cyclone position would be with the cyclone just above the spirals on the left hand side of this flow sheet, circled in white. People use sometimes normal cyclones that they can find wherever from the process. Sometimes they just buy second-hand equipment. The cyclone configuration is important. If you want to have proper desliming processes or performance, the length of the cyclone is important. The longer the cyclone, the better the performance in terms of desliming. We want to remove the fines or the slimes from the underflow of the cyclone. Remember, it was mentioned earlier that there's a bypass water effect that carries the slimes through to the underflow as well. The pictures on the top right hand side indicates underflow from a cyclone that's quite dilute. The more water that's in the underflow, the more fines reports to the underflow. The picture down below on the right hand side bottom end of this presentation shows a more optimum underflow discharge. To illustrate that via actual practice, this video shows the difference between a wet underflow and an optimal underflow from a hydrocyclone. It's therefore important that you must be able to see the underflow discharge from a hydrocyclone. If you can't see it, then you don't know how the unit is performing. Another problem with having, in terms of bypass water, is when people install a cyclone just above a spiral. The underflow is therefore kept at a very dilute concentration to allow the spiral to operate effectively. But because you are now got a dilute underflow, in this specific example of coal, the fines also is associated with high ash, as you can see on the graph on the top right hand side. So you're introducing a high ash fraction onto the spiral, which then affects the product quality from the spiral. In other minerals, having a dilute underflow going to the spiral, it affects the performance of the spiral separation process. Then there's the problem of having a coarse overflow. The picture on the top left hand side shows the view from the bottom end of a hydrocyclone. There's a nice taper, the spigot, everything looks fine, until you changed your view and you look from the top. The spigot has been inserted the wrong way. Therefore, it created an inward step just before the material is exiting the cyclone. That creates now a problem. Material is flowing down the cyclone, gets deflected by this ridge, and it's carried back into the cyclone via the air core movement. This rotational movement of the coarse material has resulted in high wear of this item, as can be seen by the strange shapes that you see on this cone of this hydrocyclone. Another problem of getting coarse material into the overflow due to the effect of siphoning. The picture on the right hand side shows the overflow being extended to down below the spigot of the hydrocyclone. As you can see by this rubber pipe that has been inserted, it has been sucked in, indicating there's a vacuum starting to form in the overflow of this hydrocyclone. It's recommended that when you have this type of installation, that a breather pipe be installed at the top of the overflow pipe of the hydrocyclone to break the vacuum effect. Alternatively, if you can't do that, is to have the overflow being terminated roughly about the center of the hydrocyclone. Let it discharge then in a tun dish so that the overflow pipe can be exposed to atmosphere. That removes the possibility of siphoning. Then you can have the underflow being discharged into a solid stream without a proper air core forming. In this video clip, you can see that the material is discharging in a solid pile, and if all the solids material cannot discharge through the spigot, it's got no other option as to turn around and leave then through the overflow. Moving on to dewatering. Dewatering, we assume a 95% mass split to the underflow, again if we don't have the size distribution. If we have the size distribution, that value will change. Often people want 100% of the solids to go through to the spigot and only want to remove water. That very seldom happens. There's always a fine fraction that's present in the overflow. Just keep that in mind. So as a safety sake, we as suppliers use between 95% and 98% recovery to the underflow. Be careful if suppliers promise 100%. It's not always possible. It can, in some cases, the hydrocyclone can in some cases be used to replace thickness. But it's very special applications, and in general, the thickener remains the best dewatering device on a process. The hydrocyclone can help with the thickener dewatering process. It cannot always replace a thickener in the process. Dewatering cyclones are also sometimes used where other dewatering equipment is not economical. Then the hydrocyclone becomes a possibility, as long as you understand the limitations. On this flow sheet, the dewatering cyclone is shown again with the white circle at the bottom left hand corner of this flow sheet, where material coming from the spiral is being dewatered and discharged then on a pad. The cyclone that's used for dewatering we refer to as a stacker cyclone. In this case, we deliberately extend the overflow to discharge below the underflow of the cyclone. By doing so, it creates a siphoning effect, and we control the strength of the siphon by introducing air, which you can see then with this bleed air assembly shown on this schematic. How this siphoning effect works is illustrated in this video. As we discharge the overflow further down below the underflow of the spigot, you can see how the discharge pattern on the cyclone is changing. And as the siphoning effect decreases, we can see again how wetter the underflow becomes. So that is the principle of using stacker cyclones. The stacker cyclone has got a flapper valve, and this video shows a proper discharge mechanism from a cyclone that's operating correctly. As you can see, there are still some moisture on the discharge pile. So you can never remove all the water, even with a cyclone that's operating with a vacuum. The picture on the left hand side shows the installation of 2 stacker cyclones. And discharge shows a good discharge. Cyclone is operating correctly. On the same installation, the right hand cyclone that's not operating correctly. And now the client is becoming frustrated, wondering what's going on, until you start to take a closer look. Overflow of the cyclone wasn't supported properly. That led to a deformation on the inlet head. Therefore, it affected the performance of the cyclone. Secondly, there was a hole that formed in the overflow pipe. No one picked it up. That hole introduced air in an uncontrollable format into the cyclone, and therefore the effectiveness of the cyclone was compromised. Then we have the odd request, where the thickener underflow needs to be dewatered further via a hydrocyclone. Now the thickener is a mechanical device. It's got enough residence time, and if operated properly, it produces a very good underflow density. So it's sometimes surprising that clients think that the cyclone can do better than a thickener, because the residence time of material in a hydrocyclone is a couple of seconds compared to a couple of hours on the thickener itself. Even if we rope the cyclone, as shown by the picture down below, the underflow is still wetter than what you will get from a thickener. Slime dam cyclones. There's going to be a separate presentation, so this is just a brief discussion on slime dam cyclones. From the flow sheet, you can see its position at the back end of the process. And in this picture, you can see the cyclones are distanced very far away from the actual operation, which now results in people that don't care or not really focusing on the performance of these hydrocyclones. If you don't take care even of the hydrocyclones that's in a remote application, you can have a situation like in this video clip, where this dam wall broke, or the slime dam wall broke in Brazil. It's not to say if you don't look after the cyclone it will always happen, but there's a possibility that it may happen. So please take care that even when you can't see the cyclones, you need to be aware of them and ensure they're operating correctly. So in conclusion, the hydrocyclone is deceivingly simple. That then results in people that once they start to gain a bit of understanding of how the unit performs, that they believe they are experts, that they believe they know where the hydrocyclone can be used. Then the hydrocyclone is not performing correctly and they get frustrated. The more time you then spend with the hydrocyclone, the more you realize there's more to this. And as you gain more experience, you get to the point where you realize, I understand now the limitations of the hydrocyclone, and then the hydrocyclone becomes a blessing. Lastly, if you want to use a hydrocyclone, decide what is the objective. Why do you want to employ this objective? Why do you want to use the hydrocyclone? For what application? Is there not other equipment? Once you've decided you're going to use the hydrocyclone, ask for advice. Don't always assume that you have all the answers. Thank you very much.